So let's add some more interesting concept called residence time. I think intuitively you already know what that means, right? So residence time is how long something resides. Where? Well, we typically define a reservoir. It could be a coastal ocean, a lake, the atmosphere, the global ocean, and so on. And you could be talking about something like a gas, carbon dioxide in the atmosphere, for example, which becomes very important when we start talking about global warming. Or it could be salt in the ocean. We already sort of implied that its residence time is very long because we said it doesn't change easily because of all the evaporation, precipitation, rivers coming in, and so on. So, in fact, the residence time of salt is a couple of 100 million years long. How do we figure this out? This is the average length of time a substance remains dissolved in seawater. In this case, we're talking about the ocean. If you have a reservoir, which is, let's say, the ocean, then you take all the fluxes that are coming in, all the fluxes that are going out. If the system is in equilibrium, then you take the reservoir size, which is, let's say, amount of salt in tons, and divide it by the flux that's either coming in or going out. It doesn't matter if it's in equilibrium, then flux coming in has to be equal to the flux going out. So the flux will be in tons per unit time, let's say tons per year, right? So if you divide the reservoir size tons divided by flux tons per year, then you have a residence time of year, right? This is how you compute residence time, very simple, except when you have a non-equilibrium situation or you have multiple fluxes, then it becomes a little bit more complicated. If the system is not in equilibrium, then you talk about characteristic response time. So the best example I can think of is when they did nuclear tests in the atmosphere in the late 1940s, 50s, when we didn't know how bad radiation was for us. People used to explode bombs and sit and watch them, right? So the radiation that was released into the atmosphere, you had to know what is the characteristic response time of the atmosphere to the radioactive material that was being released. It could also work for a ship that comes into the coast near a port and it spills some oil. So you want to know what is the characteristic response time of the circulation of this coastal region. So if you did nothing, how long would it take for the oil that was leaked to be taken out of the system, and so on. So it's a very useful concept. In the ocean, we have ions with very long residence times, and they have high concentrations like bicarbonate and carbonate. We need them. Life needs them. Ions with short residence times are in low concentration because they are quickly removed from the system, right? Long residence time means you build up the concentration. Short residence time means it gets washed out very quickly. In a steady state condition, as I said, average amount of various elements remains constant. We used the constant proportions, principle of constant proportions, to estimate salinity, for example. So just like we looked at the hydrologic cycle, we can look at the various substances that are being added and removed from the ocean. So you have the schematic here showing volcanoes spewing lots of sulfur, carbon dioxide, and so on. So you have chloride and sulfate coming into the ocean. You have rivers that are bringing in a lot of sediments, dissolved organic matter, lots of weathered material, and they are dumping it into the ocean in terms of carbonate, calcium, sulfate, sodium, and so on. And everything eventually ends up at the bottom unless it's constantly getting recycled near the surface. And the sediment at the bottom is constantly being taken down deeper and being metamorphized. It is under pressure and temperature, high temperatures. It's getting converted into rocks and limestone and other things, and eventually it's either being spewed back into a volcano or it's being assimilated into rocks that eventually form the oceanic crust, which subducts under the continents, and so on and so forth. So there is this long time scale of materials transforming at the bottom of the ocean, and there are these short time scales of materials coming either through the rivers or through the volcanic deposition or precipitation is depositing stuff. Dust from Sahara and other deserts are depositing stuff, and so on. The ocean is also producing constantly the so-called sea spray, constant waves and winds. If you live near the coast, for example, everything gets rusted eventually because a lot of salt gets deposited on everything. And the sea spray actually picks up more than 3 billion tons of salt per day all over the world, right? That's how much salt is being taken out of the ocean, but obviously either it's raining back or it's being brought back in via these various processes. So there are these geologic time scales, and there are these short time scales at which material is being cycled through the system. So we will looked at hydrological cycle where water is being cycled through the system. Here we are talking about chemical substances which are being cycled through the system. Later on we will see biological material, energy, and so on and so forth. So residence time, very important concept, and these processes that add and subtract dissolved substances in the ocean. Let's stop this here and continue in a minute on what these end up producing as profiles of substances in the ocean. This becomes very critical. We need to know how the profiles look so that when the water gets circulated, whether the substance coming from below is higher in concentration than near the surface or lower in concentration, or when the water near the surface sinks, whether it's taking higher concentration material from the surface to lower concentrations at bottom, or lower concentrations are being taken deeper into the ocean, and so on. So this cycling is very, very critical, and how long it remains is very critical. That's why we talk about the residence time.